Thank you guys for joining my channel. Today we want to discuss gas chromatography and supercritical fluid chromatography. Welcome. Generally the outline is a brief review of theory, gas chromatography, then we look at supercritical fluid extraction and supercritical fluid chromatography. Some of the further reading you can check Colu et al. On gas chromatography, that is chapter 27. Supercritical fluid chromatography, you can check chapter 29 on Colu. Gas chromatography and supercritical fluid chromatography. Let's start with the gas chromatography. It is a chromatography using a gas as the mobile phase and a solid stroke liquid as a stationary phase. So in gas chromatography, the analytes migrate in the gas phase, so their boiling point plays a role. So gas chromatography is generally applicable to compounds with masses up to about 500 daltons and with approximately 60 torr vapor pressure at room temperature. So that means that polar functional groups are trouble. Majorly, there is always a problem that arises due to polar functional groups, as we will check later. And supercritical fluid chromatography. So here supercritical fluid is the one being used as the mobile phase and a solid or liquid as a stationary phase. So in supercritical fluid chromatography, the analyte are solvated in the supercritical fluid. Then it is applicable to a much wider range of molecules. So generally some of the terms that we are going to meet, we know the selectivity, and you can be able to see what we are given there for selectivity. This is the symbol for selectivity, is the ratio of analytes B and analytes A. Then we have retention volume denoted with the V, and it is T multiplied by F. Then separation performance is always gauged by plates, which is the length of the column divided by plates or height. Then we have linear velocity of mobile phase, which is the length divided by mobile phase time. Then this is just some of those major terms that we are going to meet. If you can check from Colu table 2.26.4. So there's a lot of terms that you can find here, a lot of relationships, as you can be able to see. Then we have the theory. Mobile phase flow rates are higher in gas chromatography because pressure drops is much less for a gas than in liquid. So the effect of mobile phase flow rate on the plate height is dramatic. So lower plate height yield better chromatography. However, much longer lamps can be used with gas chromatography. So the instrumentation, this is just the basic layout, and you can see how a carrier gas get our analyte in. Then we have there is one carrier gas going in, analyte goes through the injector at a right angle. Then the column is always very long, then everything is being separated within the column, and then before they reach the detector. So you'll see that in between, or the column is in the oven. Remember, we need to vaporize. So that is why it has to be within the column. So this is generally a typical instrumentation of a gas chromatography. This sample is Agilent. So this is it generally. And then the typical carrier gas, we have helium, nitrogen, and hydrogen. The choice of gas affects the detector. So injectors most desirable to introduce a small plug volatiles the sample evenly. So most samples introduced in solution, what we call microflash injections, instantly volatiles the solvent and analytes and sweep them into the column. So splitters, we have splitters effectively dilute the sample by splitting off a portion of it up to 1 to 500 ratio. So ovens are programmable. Temperature ranges from 77 kelvins up to 250 degrees Celsius. So detectors, widely variety, we are going to look at them deeply. Then we have a Headspace, a very useful method for analyzing volatile present in non-volatile solid and liquids. So sample is usually equilibrated in a sealed container and elevated at elevated temperature. So the headspace in the container is sampled and introduced into a gas chromatography. Columns for gas chromatography, you can see we have two major types, the packed and open. As you can see, the packed and this is open. So you can be able to see also that open, we have two types. There is porous layer, open tube. There is also wall coated open tube. So open columns work better at higher mobile phase velocities. So that is also something to take note of. Then columns for gas chromatography, you can be able to see how long they are. So open tubular column, most common, also known as capillary columns. Then they are up to 150 meters long, so you can see how long they are. They can contain 1000 to 3000 plates per meter. And then pressure limit particular size in packed columns. So no A term, the AD or multipath in Van Dimter equation. Then number of plates up to 600,000. Packed columns contain packing like HPLC columns. A typical particle size 100 to 600 micrometers, then 3 meter long. So plates are 1000 to 3000 per meter. Difficult to overload. Number of plates up to 12,000. Then we have types of columns for gas chromatography. We have generally gas liquid chromatography, most common. Then we have gas solid chromatography for adsorption. Then we have fused silica wall coated open tubular columns, very popular in modern applications. Then we have wall coated open tubular. This is stationary phase coated on the wall of tube stroke capillary. Then we have support coated open tubular stationary phase coated on a support such as diatomaceous earth, more capacity than wall coated open tubular. Then we have porous layer open tubular. Then we have packed columns. So mobile phase for gas chromatography, we have hydrogen, we have helium, we have argon, we have nitrogen, we have carbon dioxide, of course liquefied. Okay, then we have gas, we have the longitudinal diffusion. That one now as we are talking of Van Dimter curve. The term in the Van Dimter equation is very important in gas chromatography. So gases diffuse much faster than liquids. So longitudinal diffusion is something that you need to really regulate. So a trade-off between velocity and plate height is generally observed. This is equivalently to a trade-off between analysis time and separation efficiency. So one, you might take longer time to get better separation, or you might take shorter time and trade off separation efficiency. So as you can be able to see in the Van Dimter curve, you have to really balance the three terms. Then we have columns and stationary phases for gas chromatography. So modern column design emphasizes inert, thermally stable support materials. So the capillary columns are made of glass or fused silica. The stationary phase is designed to provide a K and selectivity that are useful. Polarities cover a wide range. Stationary phases are usually a uniform liquid coated on the wall or packed. When the polarity of the stationary phase matches that of the analytes, the low boilers come off first. Bonded cross-linked phases designed for more robust life, less bleeding. Often these phases are the result of good polymer chemistry. So adsorption onto silicates avoided by deactivation reactions, usually leaving an this is a methoxyl group instead. So stationary phases for gas chromatography. So the target uniform liquid coating of thermally stable, chemically inert, non-volatile material on the inside of the column or on its particles. So polysiloxanes, for example, as you can be able to see. Then so these are some of the examples that of stationary phase for gas chromatography. So even the amino acids and cyclodextrins. So you can see the structures there. Then common stationary phases. For stationary phase, so these are some of the examples versus the temperatures that are needed, and so it means that what you want to use the gas chromatography to separate will determine which stationary phase you choose. So you can be able to see a range here of some of the compounds that you might want to separate versus the stationary phase that will do better, and the temperature that is working better. So temperature effects in gas chromatography very important. So temperature programming normally around can be used to speed or slow elution. So it helps handle compounds with a wide boiling point range. So newer low thermal mass system allow for fast ramps. So you can be able to see, for you to have a neat chromatogram here. So you really need to work on temperature for you to have a very neat chromatogram here. Then comparison of gas chromatography detectors. Of course, we have flame ionization. It's a universal and majorly for hydrocarbons analysis. Then we have thermal conductivity. Virtually all compounds can be used. We have electron capture, majorly for halogens. We have mass spectrometry. It's also universal, ionizable species. Then we have thermionic, this one majorly for nitrogen and phosphorus compounds. Then we have electrolytic conductivity, majorly nitrogen, sulfur and halogen containing compounds. Then we have photoionization, is also universal, compounds ionized by UV. Then we have Fourier transform IR, is also universal for organics. So that also it means that you will really need to check on your detector and whatever you want to analyze, but majorly mass spectrometry for ionizable compounds, so you will know which one is good for you. So the flame ionization detector, the most common and useful gas chromatography detector. So here the column effluent is mixed with hydrogen and air and is ignited. Organic compounds are pyrolyzed to make ions and electrons, which conduct electricity through the flame. And then advantages: it is sensitive, like 10 raised to power negative 13 grams, linear all the way up to 10 raised to power negative 4 grams, and it is non-selective, meaning it is universal. Then disadvantages: it is destructive. Certain compounds which are non-combustible gases do not give signals in the flame ionization detector. So thermal conductivity. Thermal conductivity is also a non-selective detector, like the flame ionization detector. Works by detecting the changes in thermal conductivity of gases containing an analyte. So about 1000 times sensitive than flame ionization detector. Less sensitive, sorry. So flame ionization detector is very sensitive compared to thermal conductivity detector. So it is non-destructive. That is now the good part of it. It is non-destructive. Then electron capture, majorly for detecting halogens containing compounds like pesticides. So works by ionizing a sample using a radioactive material, majorly nickel 63. This material ionizes the carrier gas but this ionization current is quenched by a halogenated compound. So detect compound via electron affinity. For example, iodide is more sensitive to bromide, then to chloride, then to fluoride, in that sequence. Then so you can be able to see how just a model or a schematic of electron capture detector. So that is how it looks like. And other detectors that we look at: atomic emission detector, the plasma systems, like inductively coupled plasma, but often using microwaves, elemental analysis, sulfur chemiluminescence detector, reaction between sulfur and ozone. Then we have thermionic detector, like flame ionization detector, optimized and electrically charged to form a low temperature plasma on a special bead, lead to large ion currents for phosphorus and nitrogen. A selective detector that is 500 times as sensitive as flame ionization detector. Then flame photometric detector, specialized form of UV emission from flame products. Then photoionization detector is a UV radiation used to ionize analytes detected by an ion current. And of course the mass spectrometer, which is so powerful. So generally, how some of the examples of GC detection, where we have petroleum analysis. So an example of atomic spectroscopy using microwave induced plasma to selectively detect lead containing compounds in gasoline. So you can be able to see the chromatogram there, and the mass chromatogram, the gas microwave induced plasma responses for gasoline samples. The column used here is fused silica capillary column. So that is generally some of the things you can check. More reading from Scooge, page 710. Then some of the detectors you can also be able to see here. You can also see the ramp. This one now you can be able to see further detection, and organohalide pesticide in water. So you can see some of the results that we are seeing there. The example of dieldrin, the endrin, cysto, nanochlor, some of the pesticides that we know of are detected in water. Then interpretation of gas chromatography data. So common use develop a method to separate compounds of interest by spiking and use retention times to determine whether compound is present or not in unknowns. So watch out for compounds with the same retention time, and gas chromatography can function as a negative test, e.g. rule out the presence of ethyl acetate in my sample. So relative retention time, you can be able to work out that of analyte and that of standard. So quantitative, the covert retention indexes based on normal alkanes. So the retention index of this compound is independent of temperature and packing. And that is so important when you are doing quantitative analysis with gas chromatography. So there is already a library of relative retention indexes. Then we have purge and trap gas chromatography for volatile organic compounds. It was invented 30 years ago by the Bella at the US EPA. Principle: inert gas is bubbled through an aqueous sample. Gas carries analyte to headspace above sample through to a sorbent trap. After collection period, the sorbent trap is heated to dissolve the analytes. The dissolved analytes are injected into a GC. So results: parts per billion, detection of volatile organic compounds like benzene, decades, halomethanes, etc. in water samples. So commercialized by Teledin, Tecma, the velocity, and used worldwide. Legally mandated for water analysis in many areas. Then there is what we call chemical derivatization for gas chromatography analysis. So gas chromatography is only applicable to lower molecule weight compounds with significant less greater than approximately 60 torr vapor pressure volatility. So polar functional groups reduce volatility. For other compounds, another separation approach can be used, like liquid chromatography, or derivatization can be explored. So derivatization is a chemical reaction that modify an analyte so that it is easier to separate or detect. So advantages: can lower limit of detection, increase sensitivity, can stabilize heat sensitive compounds, can avoid tailing in gas chromatography caused by on-column reactions like a carbonyl, amino, and imino. So these are generally polar groups. Then can improve the separation of closely related molecules. So its derivatization is very important. The disadvantage is require running a reaction with all its complexities. So that is the major. So it means that you really need to understand how those reactions will affect the final compound. So chemical derivatization for gas chromatography analysis. A typical derivatization reaction is silation of an alcohol. So you can be able to see here. So you have one alcohol, then we have trimethylsilane, and then you can be able to see the compound that we have made, and you can be able to see that this compound is now not having OH group, a polar compound that was we are having here. So common derivatives that reduce polarity. So for alcohol groups, we need to have alkyl esters, alkyl ethers, and silyl ether, like the one we were having here. Then carboxylic acid, we have alkyl ester, silyl ester. Then we have amino, the same acyl derivatives and silyl derivatives. So then we have imino, we have silyl derivatives, then aldehyde, dimethyl acetol, then thiols, we need thioester and sellyl thioether. So you are going to realize that actually now the compounds that we could not be able to handle due to polar groups and low volatility now can be handled. Then application of derivatization and gas chromatography in doping. So example, derivatization of androgens like testosterone for gas chromatography mass spectrometry analysis. So detection limit can be as low as 0.2 nanograms per milliliter. In one procedure, derivatization with trimethylsilane is used in conjunction with a series of pretreatment and extraction steps followed by gas chromatography. So you can be able to see testosterone here, and then there's a derivatization so that the OH group is derivatized to this particular non-polar group. Then hyphenation of gas chromatography and mass spectrometry. The first useful hyphenated method, continuous monitoring on the column effluent by a mass spectrometer. So this is so important and very convenient because the gas chromatography does the separation and the detection is done with the mass spectrometry detector. So very easy to interface. Capillary gas chromatography columns have low enough flow rates, and modern mass spectrometer systems have high enough pumping rates that gas chromatography effluent can be fed directly into the ionization chamber of the mass spectrometry. So for electron ionization and chemical ionization, so larger columns require a jet separator. So most common systems used quadruple or ion trap mass analyzers. Then supercritical fluid. Phase diagram show region where a substance exists in certain physical state. If we really remember this diagram, we call it phase diagram for carbon dioxide. So beyond the critical point, a gas cannot be converted into the liquid state no matter how much pressure is applied. And that is very important. So you can see supercritical fluid. So this is the region where a gas can be turned to solid. This is the region where it is a liquid. This is the region where it is a gas. Now, supercritical properties of carbon dioxide. So the fluid intermediate between a liquid and a gas, so obtained in a not so sudden manner. There is no real transition, so you can be able to see so you can be able to see photos of gas carbon dioxide as it goes from a gas liquid to a supercritical fluid. So that is it. So you can see one where you can still see meniscus, and then as you increase temperature, you can see what is happening. Then increasing more temperature, then even if you increase more temperature, now it is not turning into gas. so it is purely fluid. So you can be able to see the meniscus separating fluid and gas, but as you increase temperature, we find that less and less gas are forming, and at this point now it is fully supercritical fluid. So extraction with supercritical fluids. Why use supercritical fluid extraction? So supercritical fluids can solvate just as well as organic solvents, but they have disadvantages. There is what we call higher diffusivities, lower viscosities, lower surface tension, inexpensive, pure, easy to dispose of. So basic utility, many of the same features apply to supercritical fluid chromatography. So we introduce them here with supercritical fluid extraction. So extraction with supercritical fluid, pure carbon 4 is able to extract a wider range of nonpolar and moderately polar analytes. Modifiers such as methanol can be used to help solubilize polar compounds. Other supercritical fluids can be used. Note that ammonia is reactive and corrosive, while nitrous and pentane are flammable. So some uses of supercritical fluid extraction: environmental analysis, total petroleum hydrocarbons, polyaromatic hydrocarbons, organochlorpesticide in soils. Then in food industry, we have extraction of fats, extraction of caffeine. Then density stepping supercritical fluid extraction used as a form of mini chromatography. Then supercritical fluid chromatography is the next logical step from supercritical fluid extraction. So a supercritical fluid is used as the mobile phase. Hardware is otherwise similar to gas chromatography, as you can be able to see. Then control of pressure in supercritical fluid. Pressure affects the retention factor, which is K. Why? The density of the supercritical fluid mobile phase increases with more pressure. More dense mobile phase means more solvating power. More solvating power means faster elution times. Changing the pressure in supercritical fluid is somewhat analogous of changing the solvent gradient in liquid chromatography. So it requires some knowledge to be able to control pressure in supercritical fluid chromatography. So you can be able to see this and that, linear pressure, and this is isobaric. So you can be able to see isobaric here. We are keeping the pressure constant, and the linear pressure gradient. You can see how the different chromatograms that we are obtaining. So can be able to choose for yourself. Then detectors for supercritical fluid chromatography. Detectors are generally similar to those used in gas chromatography and liquid chromatography. Major advantage of supercritical fluid over high performance liquid chromatography is supercritical fluid chromatography can use the universal flame ionization detector as a detector. So majorly that cannot be used by HPLC. So supercritical fluid can also use UV and infrared detector and fluorescence detectors. So it is like it is more it is better. Supercritical is compatible with mass spectrometry hyphenation, so it is very nice. Application of supercritical fluid chromatography. It consider speed and capability as well as expense. So with supercritical fluid you will get good speed and at less expense. So you can be able to see. Then these are, we have just provided some of the reference materials that you can use to for further studies.